Engineering Department, Hank Lee. So Hank,
Yeah. Okay. All right. Thank you, Christos. Hello, everyone. Yeah, I'm Hank Lee. I'm the new department chair of nuclear engineering. I joined UNM last August, and still I have not seen many people on campus, so I have to see the persons in person. And today we have Carl Willis. He's our lecturer, and he has very interesting story about nuclear reactors and many interesting things. He also visited Chernobyl several times. So yeah, maybe some other time we will have some opportunity to listen his story at Chernobyl as well. But today he is talking about our nuclear reactor. On our campus, I don't know how many of you know that we have a nuclear reactor, but it is not dangerous. Of course, it is totally safe. It is for research and education. So he will introduce the reactor today. Are you ready, Carl?
I'm ready.
Great, and take it away.
Well, thank you very much, and I appreciate the School of Engineering for hosting us today and the Department of Nuclear Engineering for supplying vast talent in the form of our student operators who are here today as well. So before I go any further, just a word about myself. I'm Carl Willis. I'm the Chief Reactor Supervisor for this facility now, and I take it over from Bob Bush, who's a very competent, my predecessor, and big shoes to fill for sure. I have Robert Dwyer here on the left and Rowdy Davis on the right at our console, and they are actually going to be operating the reactor for us today while I talk to you about what's going on. So as Hank told you, I have a background in nuclear engineering that mostly has involved particle accelerator applications and radiation detection and measurement, and I've done a little bit of traveling. So yes, Chernobyl and Fukushima have been in my travel history, and I'm looking forward for the pandemic to end so that we can go do some more nuclear tourism. But on the same note, the pandemic's also given us some good opportunities for outreach, such as this event. And in lieu of bringing people into the reactor, which is something we do, this is an opportunity to bring the reactor to you, wherever you might be. And I appreciate the interest in this event and look forward to your questions later. So I'm going to show you a few slides, just talk a little bit about the history and a little bit about how this reactor actually works. And then we're going to get into an operation and actually show you how this reactor produces a chain reaction. So I'm going to share my screen, and this is where we're going to start. So there we go. Obviously, the introduction here, 5 watts and made of plastic. So we are a very small reactor, and that's represented by our licensed power level of 5 watts. And the reactor core is in fact made of plastic, and we'll get into that shortly. So you'll notice also from the aesthetic of this whole thing that we are talking about a reactor that was built in the 1950s. And that's special to me because it imbues this reactor with a certain optimism and really a sense that the reactor belongs to everybody, that this is a technology that is going to become widespread and used broadly. I still think that happens to be true. I still think it's important that nuclear technology is embraced as a part of our our capabilities as a society. And so that is really the age of optimism that we're going to find this reactor's lineage. So a little overview, 5 watts, I'm just going to put that in perspective for you. Then we're going to talk about where this reactor came from, what it was intended to do. And then we'll do sort of nuclear physics 101 for a very general audience, but I'm not going to spend a lot of time on it. I'm just going to give you a light overview. Then we've got our live demonstration. We're going to take this reactor up to power. You're going to see subcritical multiplication. You're going to see supercritical exponential rise in neutrons. You're going to see the reactor operator stabilize the reactor using the control rods we have. And then we're going to do a shutdown for you. And then we'll take some questions. So when we think about nuclear reactors, what comes to mind? Well, probably we think on the very largest scales, like this, which is one of the units at the Palo Verde nuclear power plant. This is a 3 billion watt reactor. And so we're accustomed to thinking of nuclear power plants, nuclear powered ships, things like that. And we know here in New Mexico, about 20% of our energy does come from nuclear power. In fact, it comes from Palo Verde. So this slide's a little bit dated, but the broad sense of it is still the same. So Palo Verde is over in Arizona. It's our nearest nuclear power facility to Albuquerque. A lot of students go on and have jobs there. It's the most powerful nuclear power plant in the country, and it generates 12 billion watts of thermal power over the 3 reactors that are there. Now, only about 3.9 billion watts is turned into electricity. So that gives you an idea that this is about a 30% efficient operation. The rest of that energy just goes up into the atmosphere as waste heat. So that's just the thermodynamics of the situation. And that's a power reactor. But I want to bring your attention to the fact that there exists in this country a large number, it is dwindling, but we still have several dozen, non-power reactors, reactors that do not generate electricity. And why do we have these? Well, they're used for educational purposes, neutron sources, maybe to produce radioisotopes. There are 31 that are licensed. I think there's 29 or 30 of those are active, meaning they're actually capable of running. The highest power is over in Missouri. That's 10 megawatts. And if you compare that to Palo Verde, you'll see it's still a tiny fraction of what a power reactor produces. And the lowest power reactors are, of course, right here in Albuquerque at UNM, and also at Idaho State and Texas A&M, although theirs is not currently running. And we have what are called the AGN 201 reactors licensed for 5 watts. Just to put things in perspective, if you are accustomed to cuddling your kitty cat at home, that cat is putting out about 10 watts of heat energy at rest. We're talking about heat energy. We don't generate electricity, so we put things in terms of the thermal power. A mouse is half a watt, a rabbit is about 4 watts, and a human being at rest is generating about 100 watts. And this is important in the air conditioning business. They have to account for the heat load of human beings. Now, our little reactor lands right there, right next to the bunny rabbit at 5 watts. So if you could imagine cuddling a little pet bunny rabbit, that is what 5 watts of heat feels like. That is what our reactor would feel like in your hands. Now, you would get a massive dose of radiation doing that, but that is how much heat it produces at licensed power. So benefits of being small, well, we're safe. We have low excess reactivity, meaning we don't have a whole lot of fuel around here, and we have low fission product inventory. We don't generate a lot of radioactive waste. And this means that our operation is hands-on in a way that large reactors cannot be. We don't ever have to refuel. Last year, we burned 11 micrograms of uranium. We have 700 grams of uranium. We could run this reactor basically, well, I don't know how long that would be. It'd be long after we're all gone. So we have this minimal generation of radioactive waste. We don't have to cool this reactor. It is naturally cooled. And because we don't have that active cooling system or the radioactive waste or need to buy fuel, we are low cost. So that gives us time for our core mission, which is teaching and training. And what I mean by hands-on is very literal. This system is capable of being handled by your hands. So you can actually get students to take this reactor apart, put it back together. In fact, one of the experiments we do is a hand-loading approach to critical, where students actually will stack up the fuel of the reactor, and at each piece of fuel they add, they look at the neutron population in the core. And so we can see a rise in neutron population as you add more multiplying medium, more nuclear fuel to the reactor. But you can see from these photos, we can stand in the reactor, look right down into the core, and unlike Chernobyl, we're not going to die doing that. And we can actually handle this fuel with, we use gloves because that's good just to keep the contamination off, but you can just handle it with your hands. Okay, so a little bit of history here. We do come from the 1950s, and this was sort of the high atomic era. And so the whole purpose of this reactor was to go off and evangelize the good news, if you will, about nuclear technology. So its origins were basically just a decade after the first applications of nuclear technology in wartime. And so now we're in the atoms for peace era, and everybody should have a nuclear reactor. There's this sort of democratizing influence where we want to teach people how this technology works. So as you can see, the company Aerojet General wanted to make these reactors mass produced. And to some extent, this vision came true, but they only made about 14 of them, I think. So as for a mass produced reactor, I guess that's pretty good. Cost $95,000. And that's included the lease for the fuel. And now $95,000 buys you double wide, barely. Not even, you don't even get the land. You just get the trailer. So this came from an era of extreme optimism. And the idea was, as I said, it would go all kinds of places and do all kinds of things. So this is the only reactor that has operated at a state fair. And I'm going to show you that this was in Oklahoma. It's also operated at conventions. So this reactor has been, this operated the Atoms for Peace Convention in 1958. Closer to home, it operated at the Philadelphia Convention Center. And what they mean by portable, I mean, you can see they're carrying it with a forklift there at Colorado State. So Oklahoma State Fairgrounds in 1957. Philadelphia Civic Center, MLK spoke here. The building's no longer around, but anyway, there was a nuclear congress in 1957. They actually brought one of these reactors there and powered it up. And then we, of course, got one at UNM, and we got ours in 1966. It came from UC Berkeley, and you can see that things were a little different back then in terms of how the fuel was transported. So this is a Presto brand pressure cooker that brought our fuel here to UNM from California. So let's just talk a little bit about what goes into a nuclear reactor. And I want you to think of other chain reacting systems that might be a little more familiar, like fires. When you build a campfire, you have a fuel, and by controlling the configuration of that material, you control the chain reaction that constitutes the combustion process. Epoxies are a chain reaction. The COVID pandemic is a biological system that is, a chain reaction. So what do we need to make a reactor? Well, we need our neutron multiplying medium, our fuel. We need a neutron source. We need a control element so we can actually control that reaction, and a neutron detector. And our operator is going to use the signal from the neutron detector to control the reactor and stabilize the reaction. Now, just for his benefit, some people would say this is not strictly necessary, but it's a very good idea. Some radiation shielding to protect our operator from the biological hazards of radiation. So here's a tabletop reactor from the good old days. Actually, maybe these were not so much the good old days as the bad old days, but this is a recreation of Louis Slotin putting together a fast reactor on a bench top. And so we got a multiplying medium. It's a ball of plutonium for Mr. Slotin. His configuration control happens to be his hands. He's controlling a reflective medium with his bare hand and with a screwdriver. Neutron source on the table, it's a radium beryllium. Ours here is a plutonium beryllium source. And under the table is a neutron detector. So all of the elements we just talked about are there, except for the shielding, which is too bad for this guy. So in our reactor, we have our little core, which is about 25 centimeters tall and 25 centimeters in diameter. So in other words, you can hold the whole thing in your hands. Outside of that, we have control rods that enter from the bottom, and ours are actually fuel. They're nuclear fuel. Outside of that, we have a graphite reflector to improve the neutron economy. Outside of that, we have lead, which is, everybody knows lead's a pretty good radiation shield. You wear the lead blanket at the dentist and so forth when they're taking x-rays. Well, we have a 10-centimeter lead blanket to cut down on some of those gamma rays. We have a water tank, 1,000 gallons of water to capture neutrons. And then we throw up a shielding wall, which allows us to run at 5 watts rather than the original design power of 100 milliwatts. So before we get to the experiment, I want to say there are ways that you in the audience can get involved with us here at UNM. You can come work with us. So we actually have an active job posting. This is for a laboratory supervisor. So if you want to come learn how to run this reactor and do it professionally and get paid to do it, please check out our link there. Of course, we are an educational program. We have classes, so there's a link. And I am always looking for opportunities for outreach. So my email and phone number are there. Okay, so let's do an experiment. And we're going to do what's called an approach to critical. We are going to change our reactor configuration to change the multiplying rate of the neutrons in the core. And we're going to show you subcritical multiplication. We're going to show you criticality. We're going to show you criticality or supercriticality, and then we're going to shut down. But all of this harkens back to the very first experiment ever done with a nuclear reactor. And this is the chart recorder log from that way back in 1942. And so what they did is they pulled out a control rod and they saw a rise in neutron population, but you'll see that it stabilizes over time. This is called subcritical multiplication. Then they pulled out another control rod and we get a larger neutron population, but again, it stabilizes. So we're still subcritical, but we're multiplying more neutrons. They pull it out again, we get that upside down, that concave down curve. And later on, we get exponential growth. They finally made this reactor supercritical. And then we shut down. So that's what we're going to do today. And I'm going to go ahead and bump on out of that. So we're going to go ahead and get started with our operation today. And we're going to probably take about 20 minutes with this, and then we'll move into questions. So our reactor has undergone our checkout procedure for the day. Our operators are standing ready. And let me just explain a few things about our reactor. So this is our shielding wall. Let's see. People can see me here, I think. This is our shielding. So all of that fun stuff that I showed you earlier, the core, the reflector, the lead shielding, the water tank, all that is behind here. So unfortunately, you get the nice boring view of a big concrete wall. If you were a gamma ray, this would look quite different, but fortunately, it just looks like a red wall. We have an experimental facility that is called the Glory Hole. Right now, there is a cadmium rod in it. And just like that first nuclear reactor in Chicago in 1942, we are going to pull out some cadmium and you're going to see neutron population rise. Over here at the console, the left side of the console is all our neutron detecting instrumentation. It's all X-core sensors, mostly boron-lined ion chambers. And we're looking at current caused by neutrons interacting with the material in those detectors. The controls themselves for our control rods are right here. So when you see the operator move the controls, you're going to see changes in neutron population. And so the operator has a screen you can look at. This is actually an auxiliary detector. It's not part of our licensed tech spec required instrumentation, but I'm actually going to periodically show you the screen from that detector. So let's take a look at it right now. You can see that we do have some neutrons in the core, and that is, so we've got neutron population on the vertical axis and time on the horizontal axis. And so as time goes by, you're going to be interested in seeing what happens to the neutron population. So we've got that, and I think I've got a nice close view that I can show you of the operators doing their thing. So let's see, lean in, guys. Yeah, there we go. We can see them. Might be a hair bright. I'm gonna turn this down. So, okay. And this will give you a good view of our channels 2 and 3 pico ammeters when we're running. So anyway, that's an overview of our demonstration. And then without further ado, I will go ahead and get them to start up. So we're going to take out the cadmium first, look at the growth in neutron population. Then we're going to take out our rods and just take it up critical and probably, how about 4 watts?
Okay.
Sound good? Very good. Administrative. That looks good. Demonstration 6:30. Okay, good to go. And I'll be your reactor assistant. So, or actually I'll get Robert to do that.
Yeah.
So he's going to pull out our cadmium, and while he does that, I'm going to So he just pulled the cadmium out, and we have seen a sudden jump in neutron population because there is that cadmium's been removed, and that the cadmium is a neutron scavenger. It's been eating up neutrons this whole time. So now that it's out, we have longer fission chains that are creating more neutrons. And so now, let's take a look at my other camera view here. And our operator is now going to take a needed measurement. That's what he's doing. This will take a minute, 1 minute exactly. That is a fission chamber that is counting for 1 minute, and they're going to compare the readings they get to previous readings to make sure our instrumentation is working properly. I'm going to put something under the camera here because I think, there we go. Safety rod 1 is now going in. So they're putting in a control rod right now. And while they do that, let's go ahead and look at this screen. And you can see that our neutron population is coming up a little bit. And when you think about what this looked like on the very first nuclear reactor, we're seeing the same process. This is really the basic process that a nuclear reactor does. It multiplies neutrons. So these rods take 1 minute to insert, and he has to insert the 2 safety rods before he inserts the main control rods. So he's waiting for a red light to show up here. I see a comment from Tony. Can we go to full screen? I'm not quite sure if that's if we're not able to see the full screen on the audience end. Oh, we fixed it. Thank you, guys. And by the way, Courtney is doing a fabulous job behind the scenes of coordinating all of this and making sure the stream is working and the technology is working. So I am deeply grateful for that. So you can see our neutron population has climbed from an initial value that was 2.5 e to the minus 11 amperes on that particular detector up to about, looks like about 6 times 10 to the minus 11 amperes. So we're measuring electric charge that is released when neutrons interact with the detector medium. And that will mean something to some of you and will not mean things to the rest of you. So Bill saying as a question, the red light indicates what exactly? The red light indicates that the rod has reached the upper limit switch. So the upper range of motion, reactor accident impending. No, absolutely not. So a reactor has numerous safety mechanisms so that it won't have an accident impending. It's very good at keeping itself safe. It's in fact a brilliant little design. And so now we have safety rods 1 and 2 fully inserted. They're making a necessary measurement, a rods in measurement. And again, they're going to compare these values with where we were previously. Ready to go, guys. Okay, so now you're going to see the course control rod get put in. Operator is going to reach over to the switch, flip it up, and now we have a control rod going in. It's going to take it a larger fraction of a minute to get all the way in. And again, we're looking for that red light when it's all the way up. And let's go look at subcritical multiplication. So you can see as that rod is being inserted, the operator is seeing a ranging up of the scale. So we've gone to a different scale and our trace now is green rather than yellow. But if he were to stop putting this rod in, which I'm going to have him do when it's all the way in, so just stop right there. We know that we're not quite critical because we see this concave down behavior. We see that curve flattening out again, and it is going to establish itself at some asymptotic value that is much higher than where we started, but we are still not super critical. So let's just give it a chance to settle down, and we'll see where we went. So we started somewhere around with the course rods in, we were 6 e to the minus 11. We're now 3 e to the minus 10 or thereabouts. So we have made a large change in reactivity. And in fact, what we teach our students is that in these approaches to critical, the ratio of neutron population during a change like the one we're doing can actually tell you how close to that critical condition you are, how close to a self-sustaining chain reaction you are. And when we do our hand loading approach to critical, we'll have students go up on top of this reactor. They're going to put nuclear fuel into the reactor. We close it back up again. We come back down. We do a count rate ratio measurement with all these instruments and figure out how much more uranium do we need to put in there to take it supercritical. And if we think back to the presentation slides, we have Louis Slotin, that picture of the simulation of Louis Slotin putting together a critical assembly with his bare hands. Unfortunately, Dr. Slotin died due to an accident where he dropped the reflector and made that system prompt supercritical and created a lot of radiation. When we do our experiments, this reactor is designed in such a way that we can't have that type of accident happen. But what he was doing with that experiment, he was just listening to the neutron counter click. And he knew that a particular clicking rate indicated that he was, so far, so close to being critical. Todd Murchison says, what device is measuring the neutrons and uploading for you? Well, of course, we have a beater of an old Windows, what is that, Windows 98? I don't know. So this computer, by the way, does not have any control function for the reactor. It is strictly for collecting data. And so it is measuring current in a boron-lined ionization chamber that is close to the core. And you can see that we've gotten a lot closer to critical now. It's taken a lot longer to stabilize. Just over the last minute, we've probably added about a third more neutrons. So as we get closer to critical, those fission chains that occurred long ago are still contributing to the rise in neutron population now. And So it takes longer to stabilize the closer to critical we get. Elizabeth Keller has a question. This might be silly, but is there a correlation with how many neutrons are in it and how much energy is outputted? That's a very good question. That's in fact at the heart of how we calibrate our power in this reactor every single year. We have an annual surveillance to calibrate our power measurement for this reactor. And we do that by measuring the neutron flux in the middle of the reactor with a gold foil. And we know that the fission process releases about 200 MeV of energy, and it releases about 2-point-something neutrons per fission. So we have a correlation between number of neutrons and energy released by fission. And absolutely, that is how we calibrate our power, because we can't do it thermally. We don't have any device that tells us this reactor feels like a warm bunny rabbit or something. We can't actually go feel that warm bunny rabbit. We have to rely on the neutrons. So very good question, and thank you for asking that. Not silly at all. Let's see, let's come back here. So at this point, we have one more control rod to put in, and when we put that in, we should see exponential growth in power. We should see a rise in power. We're going to take this system from subcritical multiplication to supercritical multiplication. We're going to let the power rise to bunny rabbit level. We're going to go up to about 4 watts, not quite the license limit. And then the operator is going to flatten the curve. He's going to change the neutron economy of the system so that it becomes critical and stable. So let's go watch that happen here. Let's take a look, first of all, at that last control rod going in. So guys, take it away. Find control rod going in. Somebody asked if they could see behind the red wall. Well, that would be fun. It's actually, we have a tour video that is posted on YouTube, and maybe I can pop the link in the chat later where I do show you what is underneath the reactor, and you can actually see the control rod drive mechanisms. If you go into YouTube and search, you will be able to find that. Just search for UNM nuclear reactor. So we've scaled up. We now have a pink trace rather than a green one. Fine control rod is still going in. And we are going to be looking at the shape of the curve that we get. And just like Enrico Fermi back in 1942, we'll be able to say, is this concave up or concave down? And if it's concave down, we're not yet supercritical. If it's concave up, we are supercritical. Andrei Stoyev has a question. What is the level of activity from fission products immediately after a shutdown? That's a very good question. And in terms of activity, I don't actually know. It would be a little bit complicated to calculate that because there are hundreds of fission products and we know what their distribution is, but the radiation they each emit and their half-lives and so forth is kind of complicated. So I don't know the answer to that immediately. When we do our hand loading approach to critical, we do try to keep the reactor shut down for about a week before we do that to avoid putting a lot of short-lived fission products in the fuel. So our neutron count is now going up, and that really does look like an exponential rise to me. So different ways of expressing exponents, but up in the upper right-hand corner of this screen, you can see that we have doubling time, which is a base 2 measurement of the rate of exponential rise. We have period, which is the base E, or E being the base of the natural logarithms. We also have decades per minute for those who like good old base 10. And depending on one's background as a reactor operator, you may be familiar with one or more of those more than any other. So we tend to think academically, we think about period. The folks on nuclear ships, submarines, tend to think in terms of decades per minute. And doubling time, of course, base 2 is easy to conceptualize in our heads. It's easy to see when my power has doubled. But we are now at we're now at 2 watts. And so my doubling time is 14 seconds. So, and now about 10 seconds, we will be at 4 watts. And the operator is now making some movements to correct the rise in power and limit us to 4 watts. So A valuable addition to your charts, a chicken is about 10 watts. I discovered this wonderful fact when discussing the need for heating a chicken coop. Yes, I didn't find data for poultry, but that's good to know. It seems like they're pretty energetic animals, or they have a high metabolism. Anyway, you can see the operator is stabilizing the neutron population, making it steady. And what this means is the rate at which neutrons are being lost from this system is equal to the rate at which they are being formed by the fission process. So we're at 3.9 watts. Now we're coming up on 4 watts. And while he's doing this, I think we've seen the fun part on this screen. So I'm going to pop back over to, let's look at this screen here again. And just so you know what kind of radiation level we actually operate in, I'll give you a little demonstration here. So let's take a look. Let me, actually, the best thing to do with this guy, I'm going to change my camera to that view. This is measuring gamma radiation at this point, which is, and I'll wait for the camera to catch up with where I am. There it is. You can see we are measuring 0.9 milliröntgen per hour. I still think in Röntgen units, it's a convenient unit because it's actually a measure of charge released in air. But 1 milliröntgen per hour is approximately going to give you a whole body dose of 1 millirem in 1 hour. We are allowed 5 rem in 1 year. And this is probably, we tend to measure a background of about 10 microrem per hour here. So 1 millirem is about 100 times higher than background in this laboratory. And that's what we see when we are up at about 4 watts. And we all wear dosimeters because we are radiation workers. These go off and get processed and tell us how much radiation we received. Put that back with those guys. Another thing I'll show you, we do have some neutrons in here, and we talked a little bit about how neutron detectors work, but I'll give you another demonstration. Typical neutron detector. Neutrons are not charged particles. They're neutral parts of the nucleus. And so we have to have a reaction where they are turned into charge that we can measure. So that's what this device does. It has a big old bowling ball that slows the neutrons down because they're more easily detected when they're slow. And then they're captured on boron. And that causes the boron nucleus to explode and release charged fragments, and that's how we can detect neutrons. And so this little thing is going to make a clicking sound, and it will make more of a clicking sound when I get closer to places where neutrons are. So, so we do have a little bit of neutrons coming around here, but that water tank does a good job of shielding them. Let's look at a couple more questions, then we're going to do a shutdown and talk about some get some questions from y'all. And thank you for your patience. I think there's a good number of questions from the audience. Okay, how long? This is from Josie. Oh wait. Let's see. No, I got one from Ted. Repeat a previous question. Do the operators need to change scaling in order to prevent a reactor trip when approaching full scale for a specific decade of power? What other automatic trips are involved, such as max power, rate of increase? Good question. Okay, so our operators do not have to change scale on anything. We have our the instrumentation that required in our tech specs has logarithmic readouts. So they can see these large changes in neutron population without having to change the scale. Let's see. What other automatic trips are involved? Well, we have a power trip. It's at 120% licensed power. So when we reach that limit, our rods are dropped. I told you earlier, they come from the bottom into the core. Well, if we get into any situation where power is lost, or where the reactor scram system operates, we use gravity plus a few springs to make those control rods drop. That'll happen at overpower. In other words, if channel 2 or 3 sees a signal level that's too high, a current that's too high, indicating too many neutrons, indicating that we're above our licensed power, those control rods would drop out. The actual safety limit for this reactor is 200 degrees Celsius in the core. That is the temperature above which we can't go or we start to break down our nuclear fuel and release fission products. We actually have a controlled meltdown to carry this reactor deeply subcritical if we ever reach 200 degrees C, and that is a polystyrene thermal fuse. So polystyrene it melts at a lower temperature than polyethylene, and we put more uranium in that thermal fuse. And so if we get to those sorts of temperatures, that will melt and the entire bottom of the core will just fall down, take us subcritical. So yes, enrichment level of the fuel. Or wait, let me get to Josie's question. How long after a shutdown, when would it be safe to go past the red wall? We can go in immediately after, although generally my approach to this is to wait an hour or so if we've been running at high power. We'll see dose rates of 5 millirem or so inside the wall immediately after a shutdown. Andre has another question. What is the level of enrichment of the fuel? 19.5 plus or minus 0.5% uranium-235. So we are a high assay, low enriched uranium fuel. How are such old looking required control equipment maintained? Well, actually this reactor has been through 2 instrumentation upgrades since it was original. When it was original, we had different neutron detectors. We had vacuum tube equipment. That was taken out in the 70s. Then between the 1970s and the 90s, we had a different console arrangement, and that had a big old selenium rectifier, which we don't use anymore, but it's actually still in the panel. Bad thing about that is selenium rectifiers smell absolutely horrible when they burn out. So we no longer are using that. We are now using equipment that is sort of, I would say 1980s or 90s vintage. And this console, this iteration is from the 90s. So our equipment's actually fairly recent. But whenever you make any equipment upgrade to a nuclear reactor, there's a process called 10 CFR 5059. This is changes to the facility, changes, tests, experiments. If you do anything with any of this equipment, you have to satisfy the regulators that that change is conservative from a safety perspective. This can take a long time if your ambition is to upgrade an entire suite of instrumentation that may have been there since, whenever. Okay, Elizabeth has a question. Is this reactor normally used for UNM experiments? Absolutely. I mentioned our mission is teaching and training, and we can do that very well because of our small size. So right now I'm teaching a senior reactor laboratory class where they get to do the approach to critical experiment I mentioned, where they're stacking up our pieces of fuel, looking at neutron population. We do an experiment where they activate, where they make materials radioactive. We actually do a number of experiments. So we do an experiment where they are attempting to identify unknown materials through neutron activation. This is a very important analytical technique, neutron activation analysis. And just yesterday, some students made radioactive gold. Turn on a Geiger counter here, and let me show you what they cooked yesterday. These are little gold foils. They're not showing up real well on the camera. There they are. Oops, they fell over. Anyway, gold foils. Or wait, those aren't the cooked ones. The cooked ones are, they put them over on the side here. Let me see if I can grab them. They're off screen. They're a little hard for me to get. But you can hear the Geiger counter crackle. With any luck, I'll be able to pick some of these up here. I don't want to belabor the point, but I tried to pick them up and I ended up dropping them on the floor. So anyway, we do we do some neutron activation analysis experiments. We do importance function measurements. That's what students were doing here recently for one of my classes, where they're actually measuring the influence on reactivity of the system by putting things at various points in our glory hole. Other experiments done here. Of course, we have to measure the power every year. We typically let students do that. We're activating a gold foil in a particular place, and we're looking at the neutron flux there. Let's see, other experiments. Guys, what's your favorite experiment, or do you have one? Sorry to put you on the spot.
I think approach to clinical is one is the best, but it takes forever.
Yeah, so these guys like the AGM, the approach to critical experiment, which is one of the more distinctive ones that we do. And the only problem for students is that they have to be here sometimes till like 9 p.m. to get that one done. So sometimes we'll order pizzas and have them out not in COVID, of course, but in better times, order a bunch of food, have it out in the student lounge, and they can trade off duties at the reactor versus the arduous task of eating pizza. Let's see. Vinicius, what is the commercial cost of this reactor and the time to the next refuel? Well, so we have no plans. I have no plans to refuel this reactor. The fuel that we have should last thousands of years, really. In some process other than fuel consumption in the reactor per se might lead to the demise of this system, mostly just because, we have motor drives that are made in the 1950s and things like that. So there are maintenance issues that I think about, but running out of fuel is not one of them. Commercial cost of this reactor, well, we don't pay for our fuel lease. And basically we don't maintain licenses for manufacturing radioactive materials. So our costs are very low. Now we do have maintenance that comes up. We do have to buy new neutron sources for some experiments. That's a little costly. So we spend some money, but not very much. Does the radiation degrade the material the reactor is made of? Excellent question. So the polyethylene in this reactor, and this is a dummy fuel disk, the real ones look black because they have the uranium in them. The polyethylene is what they call radiation stabilized. This means that it has actually been treated with radiation to improve its physical and thermal properties. So, but you're right, if we were to take polyethylene and put it in a very high powered reactor, we would cause nuclear, we would degrade the bonds that actually make this a polymer with certain properties. In fact, in the extreme, we would dissociate it into hydrogen and carbon, and it would lose all structural integrity and turn into gases. But at the low sort of 10 to the 8th neutrons per square centimeter per second type flux level that this reactor operates at, we don't have to worry about that material degrading too much. What's in the bucket? I don't think there's anything.
So in order to do maintenance on our water flow currently, we need very long gloves because the water is disgusting.
Oh yeah, so Rowdy, they probably can't hear you because I got the lav mic on. Yeah, so he's saying that the gloves that we use to go into the water tank are in there because the water is a little bit nasty. Not radiologically, it's just it's been in there 50 years. Philip Martinez, in your opinion, what's the most interesting experiment you've performed with this reactor? Do you have any new experiments planned for the future? Well, one thing that interests me personally is reactor noise analysis. And so I've thought about ways to actually do some noise analysis with this reactor and maybe introduce that as a lab experiment. That's just one thing that appeals to me. And what this means is, our reactor is producing neutrons, but they're all time correlated with the process that created them, the fission chains. And so unlike radioactive material, unlike the clicking of this Geiger counter when I had it near the gold, the process in the reactor is not exactly random. And that difference from being random, I think, is an interesting feature to explore a little bit more. Jim Klein, neutron activation analysis. Okay, Krista's about to jump out, which reminds me, we need to shut this reactor down. We're not just going to run it all day. So let me, Rowdy, not yet. He was about to push the big red button before we were ready. So I'm going to have Rowdy push the big red button. This is called a manual scram. Send those rods out of the core. We're ready. Hit it. You'll see that the activated lights went out. The rods are dropping. And let's take a look at neutron population real quick. So this is what he is seeing right now. And one of the interesting things about this is that the power does not drop immediately. We do get a prompt drop, of course, but then we see this long tail of neutrons. And where are they coming from? Well, they're what are called delayed neutron precursors, which are actually radioactive fission products made in the fission process that decay, that undergo radioactive decay by emitting neutrons. These are extremely important in making this reactor controllable on a human timescale, but you can actually see the combined, the multiple exponential curves that are combined into this shape that we're seeing as those delayed neutron precursors decay off and get rid of their last little neutrons. Okay, so we're about to close the talk, but I figured I would try to take one more question if we could, maybe a couple more. So if anybody's got questions, please toss them in the chat, and there are a couple more. Ted, do you have a reactor safety subcommittee for review and approval of procedures? Yes, so we have what's called an RSAC, our Reactor Safety Advisory Committee. I'm going to let you watch Robert put the cadmium back in the reactor there. And the RSAC meets 2 times a year. So let's pop back over here. So we just put the cadmium in and you can see the drop in neutrons associated with it. Okay, who holds the license to operate, oversee the students? Well, that would be me at the moment. I'm the SRO, the chief reactor supervisor. There are actually 4 SROs currently. Must he always be present when the reactor is in operation or just during startups? Very good question. So at our facility, the SRO only needs to be present for startup and intentional shutdown. He does not need to be present during routine operation, although practically we don't operate long enough that it makes sense for there not to be an SRO on site. Okay, any other questions? I see we still have 2 minutes. We actually have 2 minutes. And so if there's any more questions, let's try to take care of them here. Let's see. Here we go. Thank you, Dr. Lee. Really appreciate your patience earlier as I was getting set up, and good to be here. Elsa Castillo, History of Nuclear Engineering as a Career. Fascinating topic today at 4 p.m. So make it an all-day UNM School of Engineering virtual field trip and pop on over to the link that Elsa has kindly shared. Bill Sang, excellent overview, nice talk. I'll never look at a bunny the same way. That was the idea. That was what I was thinking. Well, and guys, thank you very much. And gals, I really appreciate the opportunity to do this. And as I said, if you can think of other ways in which the nuclear engineering department can work with you on outreach, I would welcome the opportunity. My email, carlwillis@unm.edu, Carl with a C. Would love to find ways to work with you on new experiments, to work with you on outreach, to have you come and apply to the job we have posted, to have you here as a student. So thank you very much for your wonderful attention, and look forward to the next time.
Thank you for your presentation, and thank you for showing us the nuclear reactor. And thank you for everybody who attended the talk today. We hope you enjoyed your time with us. Our next Engineering in Action talk is on April 23rd, but this time it'll take place at 3:30 p.m. The topic is the virus-killing possibilities of UV light in polymers. And also don't forget to check out, as mentioned before, the history of nuclear engineering. The link is in the chat. And everybody have a great weekend. See you then. And as always, go Lobos.